Welcome to lecture number 4 of module 3. In lecture 3 just we saw the static responses as well as the dynamic responses for the step change in the frequencies, basically the step change in the load, and there was some change in the frequency, and we found that there is some steady state error, and that error is going to be 0, so that we have to do some control action, because our intention is not to meet that load whenever it is changed. It is also that we have to bring back the frequency to its normal or rated value. So if we see here, strategies I derived this expression of the frequency, that is a time varying frequency. Here we ignored the time constant of your turbine and governing system, and then only we took the power system time constant, that is a TP, we consider, and then we derive the simplified dynamic response. So this frequency, you can say it is this x, that is a change in the load. X is nothing but here x is your change in the load, the magnitude, how much you are changing with the step that we are talking. It is not a gradual change, it is the step change. If your load is gradually changing, then what will happen? This load will be met by the governing system as well as the net load release, and this frequency error will be not maximum. But here what we have assumed, this is your sudden change in this your PL, and this is called step response. So here this is the negative sign, shows that whenever there is a load is increased, that x is positive, this frequency will be negative. Change means it will be lower frequency, and it is, you can say, exponential 1 minus e exponential minus t upon tau, and the tau is the time constant. So you can see the frequency response will be here, it will follow this curve, and that is shown here. Now you can see the time constant of this whole response is now 0.3 second. This 3 seconds we consider when the TP was 20 second for the previous examples. In the lecture 2 I considered one example. For that case, if you consider your R, Kp, D and your Tp, then we will get the T is approximately 3 seconds. So we can observe from here there is always steady state error. Means here this is your steady state error is existing. So from this, if you are ignoring this your governor time constant as well as the time constant, then you will get the response like this. But if you are not ignoring, if you are going to consider that, then your response will be slightly here, and like it will be settled here. And again, how much ripples and how will be the overshoots and the peak overshoot, etc., is decided by the time constant and the gains, etc. So here we can see that we don't want this steady state error. We want that once load is changed, the frequency should deviate. Of course, if frequency will deviate, then only the governor as well as net load release will act, and then we want that it should come back to the system. For example, I want here this graph for the frequency change. Let's suppose load has increased, so I want that here frequency should go back and settle to its normal value here, that is your change in F is 0. So it should come, and then finally we want that it should go to the normal value. We want that. Hence, a use of secondary control is required to eliminate it, and we will see the secondary control loops. So this loop which we discussed so far here, that is your primary ALFC loop, that is automatic load frequency control loop. Some other observations that you can make it from here, and those are that you can see that the overall closed loop system time constant is approximately here, it is a 0.3 second, and which is less than the time constant which we consider the open loop transfer time constant TP, it is 20 seconds. So from the 20 second it has come to 0.3 second, so there is a response becomes very fast compared to this 20 second. So that is very, very good achievement. This speed up is a result of feedback arguments, that we had the feedback argument of the speed governors. Means we had some arguments. For example, you can see here, thus I can say here this is your the turbine and governing transfer functions. I can say GT, and here we have multiplied by your GH, Then we are having here your GP, if you remember, means this GP is the transfer function of power system including your damping, and here this is your change in F, and that is here coming through 1 over R, that is a, and finally here that is coming to be here, and this is your change in PC, and this is here it is negative, this is your positive. So this is we are having one loop. So it is a possible if we are not having this feedback loop, and that here that feed loop is provided by the governor here, that's R, that drooping characteristic. So this value is only trying to reduce and try to speed up that the change in the frequency that regulation governor will take action. So if it is not there, then the time constant of whole this will be the same, just 20 seconds. Here they are very fast and they will die out. And here of course we had this change in the loading, that is static loading. So here I want to say that the speed up is a result of a feedback arrangement of the speed governor, means that here the feedback arrangement I am talking here, this is you can say the feedback here from the frequency is coming here, and that's why we have improved the time response. That's the time constant of the closed loop system now has become 0.3 seconds from 20 seconds. So it is great improvement. And now the system can be made still faster. We can reduce the time constant, and then by reducing R. Wow, you can see here this R, the time constant here you can say coming into the picture here is R directly inversely here the proportional to this. So what is happening, you can see if you are reducing this, the Kp is very large value, so it will not affect much, but this value if you are reduce, then what will happen, your T will be also reduced. So therefore if you are reducing R, then you can see what we are going to get, this your system response again becomes more faster. And also the advantage of this, the reduction of R also reduces the static frequency error, because you can see your static frequency error, this if you remember this formula, this is nothing but your 1 here, that is change in your PL, or you can say X, divided by your D plus 1 by R. So what happens if you are reducing this term will becomes larger, reduction of R will give larger value of here your denominator, and larger value of denominator will say there is a less value of SS, the frequency error. So this is also another advantage we want. We are having, by reducing this, we are reducing the static frequency error, that is very, very good. So another observation we can see, the inclusion of turbine and governor time constants, the response will not be exponential, and here it will be, as I said, it will be some oscillatory nature here will get, and it will be settled in the few milliseconds, and finally you will get the steady state error here. Now with this what we have to do, now we have to design the control law or control strategy, and we will see here. Let us see the physical interpretation, how whole this control loop is working. For that, let us consider the load is suddenly increased by 1%. Again, change maybe your positive side or negative side, means you can increase the load, you can reduce the load, but here I have considered that the load is increased by 1%, and if you will consider the lecture 3 problem where it was 20 megawatt load was increased, we are considering, and for this what will happen? First, this load is increased, means load switch is closed, means you are going to draw more load. The governor and the net load release will not act. This load is met in the few milliseconds by the kinetic energy stored in the system. So once the kinetic energy is released, then the frequency of the system will fall, and once it will fall, then your governor, because the governor works on the change in frequency, if the frequency is not changed, governor will not work, because we have assumed the raise and your lower commands are fixed. So then your governor will come into action, and it will try to supply power to the change in the frequency. Similarly also your this net load release means, as I said here, this your change in the this power. Here it is nothing but I can say it is D into your FSS, that is minus here change in your FSS divided by R. So this is due to the governor, this is due to the net load release. So whenever there is a change in the frequency, so first few milliseconds there will be no change and the kinetic energy will be supplying this load release, this demand, and then frequency will of course fall, and once there is a fall means there is a change in the steady state frequencies, then here we will get the net load released by the load components, and here the governor will come into the action and it will try to provide power and it will be giving power to this. So these are things, and also I explained in the previous lecture that this component is very small. We saw in the previous lecture this is for this 20 megawatt it was the supplied by here release is only 0.5 megawatt and this was giving the lion's share, and here it is a 19.5 megawatts approximately. Here it was also we made some approximation. So you can see this component is less, but still it is 0.5 megawatt is not very less, but compared to this it is very less. So now what we have to do, now we have to go for the secondary area here automatic load frequency control loops, and then we require some control system specification. Those are, first we have to design a control loop that must have the sufficient degree of stability. So the control loop here must be sufficient, must have the sufficient degree of instability. Also, following a step load change, the frequency error should return to 0. This is known as the isochronous control. So this requirement must be met. I'll come to again. Here second is your integral of frequency error should be minimized, means we are integrating the frequency error, that should be always every time minimum, so that we can return it to the system, we can return it to the 0 error and it will be better. Another, that the individual generators of that area. So far we are discussing the single area concept, means in that area all the generators are participating. There may be possibility the multi-area system, means where the different areas are connected with the tie line. We'll see in this next slides. So the individual generators of area should share the load for the optimum economy, means we have to change the loading. Suppose the load is increased, suppose load of 20 megawatt is here increased, then we have to share this load to the various generating stations so that we can achieve the minimum cost of generation, means you can say economic load dispatch must be done. So this is basically at the later stage, but first for the control here we these three specification along with another specification normally we go for that here this overshoot, that the system overshoot should be minimum. So I can say here, right, this system overshoot should be minimum, because what will happen if your overshoot is more, there is a possibility that it may create lot of problem. Always we try to have the minimum overshoot, and also the settling time that should be the fast enough, and then it is called your control specification. Now to come to this first point here, what we can do here, this control loop must be sufficient large. For this we can say always the stability is the governing criteria. We must assure that stability system closed loop must be stable. So the stability is always a problem in closed loop control. The tighter error specification, the greater risk of a proposed loop will turn unstable. So if your specification is very tight, means your error tight is very, you are putting in such a fashion that it should suddenly change the error 0, then there is a possibility that your closed loop system will be unstable. So we don't want your control loop system should be unstable. So we have to be very careful about the stability, and always it is a concern in this closed loop system. Open loop system may be stable, but it is not necessary, it is not guaranteed that closed loop system will be also stable. So we have to decide the gain and time constant etc. of your control loop so that we can get the sufficient degree of stability even though in varying operating condition. Second is that the need for the frequency constancy, as we note that if there is a change in the load, the frequency error should return to 0. And here this is called your isochronous. Iso term is basically used. Iso means here it is a constant, and here the chronos means time, means it is a constant time. So we want that no control system can, however, eliminate the transient frequency error. Here we are talking about the frequency error should return to 0, means your static frequency error. The transient, or you can say dynamic frequency error, cannot be 0. No control system can do this one. For example, let's suppose here, as I said, we are having the response like this. Here we want that this error should be minimized. So what we can do, we can here, it can go here and then it can settle. So you can say here still we have some error at the beginning. So this is a transient error. So transient error cannot be minimized. Means if you want to have this one completely from here, even the load is increased and this is your 0, then we can say your transient error as well as your static error is 0. So it is very difficult to achieve, it is not possible. So what we normally consider, we consider that your steady state error must be 0, and also we have to consider that this overshoot should be minimum, and also the settling time. Means settling time, as you know, the settling time here, it should be as minimum as possible. Then we can say our the control design control loop is the best one. So now integral of frequency error should be minimized. Means what we are going to do in this transient frequency error, as I said, it is not possible. So here the integral of this, I can say your this change in the time, that is the integration of the frequency naught, here integration of change in frequency with the dt, and here from 0 to the time, this we want to minimize. So this change in the time, that's a time error, can be expressed in the seconds here, and here we want to minimize, so that how fast. This basically shows that how fast you are achieving. Means this means there is a possibility that we can achieve here, we can achieve suddenly here, or we can achieve here and then here. So you can see this is taking more time, this is taking less time. So we are here, the integral of frequency error should be minimized, means we are just achieving in the minimum time, this time just we are minimizing. So that is also required, and that gives you another criteria. And as I said, the economic concern is only later on. Once we have designed this control, then we have to decide that which generator will be loaded how much, and then so that we can achieve your economy, or you can say minimum cost of generation, and that is very, very good. So in this secondary ALFC loop, there are the various type of controllers are possible. Controllers can be here your the proportional controller, can be your integral controller, and it is also called the reset type. It can be your PI, that is a proportional integral controller. This PD controller, it is your proportional differential controller, and the PID controllers are possible. So there are certain advantages over other controller. Again, we will see this type of control when we will discussing about the excitation system control, that we will compare there. But here this is a reset type because our error is every time existing. So our here criteria and concern is that we have to use some reset type of controller, so that we can, the change in error, static error, is maintained to the 0. So we use the integral controller. So only integral type of controller is used because it reduces the error, because our here criteria is to reduce the error, and then we decide the gain, etc., so that we can stabilize your closed loop system should be stable. So here you can see how we are going to add that. In this you can see now, so far here from this block, from here you can see this is your nothing but your primary ALFC loop, primary automatic load frequency control loop. Now here we are adding this P reference, that is a PC we are going to change, and here that frequency we want that it should be integrated. Here you can say integral controller. The negative sign here shows, as you know, we require when the frequency is negative, we require the P reference should be positive, because when the frequency is less, we must increase the power. So here the minus term is used. Ki is a gain, and here 1 upon s shows that it is your integral type, means this type of controller. So the control specification, again I can just recap that it should be stable, there should be minimum overshoot, and the steady state error, here is talking error, must be 0, and that is should be isochronous control, means equal time control. Here that the change in the power now, we are the raise and lower command, that can be given one command, and based on that we can use, and this is a negative of integration of ki1 gain multiplied by your change in frequency with the difference integration of time. If you are taking here Laplace transform, means we are getting here your ki upon s and here change in fs. So this signal is fed to the integrator is called area control error, means that error we are sending here so that it can minimize. So the area which is coming here, it is called your ACE, this is area control error which is coming here, this is basically here the area control error, sorry. So if we are going to add here, now we can from this, it is coming here with this block already I have used here, and then we can have secondary load frequency control loop, and then we will see now whether this loop is stable and what will be the value of ki. That is very, very critical, and it decides several things. So this ki value must be chosen to meet your requirement, and we'll see now the static as well as the dynamic performances of this secondary loop as well, along with your primary LFC loops. So the signal fed to the integrator is called or referred as area control error. So this is, sorry, this is not this. So whatever the signal which are feeding to this integrator is called your ACE, and this is called your area control error. This is one area we are talking, so it is area 1, you can say. If you are going for the multi-area, we'll see the area control errors for the different areas will be the different, and then we have to use controllers for reducing that. Now let us see the dynamic performance or static performance of this one. First we'll see the static performance, then we'll go for the dynamic performance. Now we want to completely relate. Here your output is your frequency, input is your change in the power. So we have to write this, the transfer function, means in change of frequency, that is output in terms of input. This we can say it is your GP. This is nothing but your GHT, including I am now combining GH and GT, here GHT, and then we will see here what we are going to get. From here what we can relate, this change in this frequency, that is I can write the change in the frequency, that is Fs, it is nothing but we are getting, that is your GP, and here we are getting change in PT minus change in your PL. All these are we are writing now. I have removed here S, but no doubt these will be the S in the Laplace, we are talking Laplace domain. Now this PT, the PT change in PT is nothing but I can write here, they are coming, just first you can see from here. Here this PT is this signal and this signal, this is positive, this is negative, and then that is multiplied by the GT, and that is equal to your, here this is nothing but your PTS, that is change in here. So from here this change in F is multiplied, and then we are adding. So what we are going to get, you can see this PTS is nothing but here I am going to use the GST multiplied by the signals which we are getting, that is your one what we are getting, this change in F is of course is a multiplication of both, and then we are getting minus Ki upon S, here minus 1 upon R. So we are getting this signal from there, and that can be, here you can say we are using this. Now we can use this here. So what we are going to get now, the change in this, your GP, here the PT we can replace, that is your GST, means your GST is nothing but I can write your GH into GT, means it is a multiplication and combined I have written. So here GST minus Ki upon S minus 1 upon R, here change in your Fs minus change in your PLS. So now we can simplify this. Change in F will be going that side. So I can write this change in Fs is nothing but minus Gp here, again Gp into, I can say, change in the PLS divided by 1 plus Gp into GHT, and then it is a multiplication of minus here, sorry, plus KIS, now plus 1 upon R, because this minus we have taken that side. If we are going to here, then it will be added, means I have taken the minus sign this side and then we are sending here, so we are getting this one. So now you can see the previous case, when this was 0, we were getting this multiplied by R, and that's the same thing. So what now we have added in the previous, when this Ki integral controller was not there, then we were getting this change in F. Yes, it is nothing but your minus Gp into change in PLS divided by 1 plus your Gp into GST and into 1 over R. So we were getting this. Now this 1 upon R is added with another factor here. So this was the case when there was no integrator. In this case we have used the integrator, and then it is coming along with here this 1 over R term, and then we have to see the steady state response for this. So to this, what we can do, this change in Fss, again we can use the final value theorem, and that is nothing but I can write here the limit S tends to 0, and here S into change in Fs, means first we have to put S and then you have to put the value of 0, S is equal to 0, and then you can get it. Again here the change in PL, that is nothing but your sum, I can say change in PL constant, or X upon, you can say yes, because we are talking about the step response. So we can put this value and then we can go for this. Now you can put this value here. It is nothing but your minus Gp, and this value is nothing but your change in PL. You are multiplying by S as this term, and here it is 1 over S. Now here we are going 1 plus Gp, GST, and here Ki over S plus 1 upon R. Now we have to put S tends to 0. So if you are putting here, you can see this is a cancel with this. Now what will happen, if you are putting this S tends to 0, means here if you are putting here, we are getting some Kp, 1 over St, means only Kp we are getting. This is a constant, here it is 1. Here what we are going to get, you can see here, this is unity, means I can say Gp S tends to 0 is your Kp. Your GST S tends to 0 means limiting value, it will be your unity. And here you can put, if S is equal to 0, this is infinite. So what we are getting here, minus Kp into change in your PL divided by, here 1 plus infinite is means again infinite. So here you are getting infinite, and this is nothing but your 0. So this is our criteria that we have to get this value 0, means now steady state error here is 0 and it is required. So we can see the integral controller gives your error 0, and that is requirement, and we also verified. So this is your steady state response of this whole, this secondary ALFC, that is your secondary area automatic load frequency control. Similarly, we can go for the dynamic performance, and we'll see this dynamic performance gives several, means the Ki is very important, means playing very important role for this your performance of your dynamic response. So here this is your the complete closed loop transfer function, for which we saw the static performance, and steady state we found that here it is your 0, and that was required. Now let us see for this closed loop transfer function, means change in frequency, here is related with the change in the load, and we want to see the performance in sense of the step change of this PL. What will be the performance? Again, the Ki, let us take as a value of Ki. We will not put the exact value. To see this, as you know, what we have to do, we have to again ignore the time constants of GTs here, GST, just we can say it is very small, so we can ignore, and then we have to solve. So this simplified will be, again I can write the change in your frequency in the Laplace domain, it will be nothing but minus your GP, here change in your PL S divided by 1 plus it is your GP, and again here Ki over S plus 1 by R, and for this we have to derive the response. Here again this we want to see the step response, so the PLS is nothing but I can say the magnitude the PL divided by S. So we can put that value and we can see what we are getting. So I can again simplify this. GP is nothing but your Kp 1 over 1 plus TPS, and TP already we saw that TP is approximately 20 to 25 seconds. Here multiplied by that's just some magnitude, this PL divided by S, and that here the complete division will be divided by this. I can say here 1 plus again this Kp 1 over TPS, and we have here Ki, that is gain of integrator, this is your S plus 1 over R. So we have to again simplify this. You can see this T 1 plus TPS is here, then we can remove this. So we can write here again this, we are getting minus Kp into change in this magnitude. Here I can say this S can be taken here S, and then I can write here 1 plus TPS plus I can say here Kp Ki over S plus 1 over R, and this is our simplified again. And what now I am going to do, I am again going to multiply it by SR in all the terms. Here you can see what we will get. I can again simplify this. Here I will get plus S, and here I can multiply R, and here I can say this is a SR. So this S dot R is multiplied everywhere. So what we are getting, this S will be cancelled and R will be there and all will be going up. So I can write here Kp into R into change in PL, and here I can write this value is coming here first. So it is SR plus TP S is TPR S square. This is a quadratic term, just we are going to get, you can see here, plus here we are getting the Kp R Ki plus here Kps. So we are getting this much, you can say this is TPR S square, and S term here is plus R and plus Kp is there, and here we are getting this constant. So again we can simplify this, and we are going to get here minus Kp into R into change in PL, and I can write here the TP R S square plus here S, that is a S domain, here R plus your Kp, and we are getting some constant, that is Kp R into Ki. Now we can see this denominator is a quadratic equation, means we will have the two roots, and the roots will be, if your Tp and T are fixed, that is basically related with the already designed parameter, because your governors once they are set it is constant, but the Ki, that is the integral gain, that we can change, we can set for our the system performance. So this decides, this characteristic root of this is very very important to decide whether your system is stable or not. First criteria that we have to meet, that it must show that we are having the stable closed loop, means this loop is stable. To see this, here all the coefficients are positive. here the Tp is positive, R is positive, Kp is positive, means all the here constants are positive. So this gives one criteria that it will be, means the possibility of the stability is very large. If any one now is negative, then it will be unstable. One root will be lying in other left, you can say right hand side of the S plane, and that is not required. Again, the right hand side, you know, here in the S plane, if you are talking, this is your left hand side. So all these here roots must this side, and this is your called right hand side. We don't want here unstable side, here is a stable side. To see the performance, we can again draw here the characteristic equation, and then we can decide what should be the gain, because this Ki critical is very, very important, which decide the criticality and the overshoot and underdubbed performance of this. So here just it is a denominator, and this is also known as a characteristic equation. This gives information whether your system is stable or not, and for this let us see here what we are going to get in the characteristic equation. If we will solve this, what we can say, this S means I can say your here this equation which we wrote here, that is a Tp Rs square. I can say this, I can write the Tp Rs square plus S R plus Kp here plus your Kp into R into Ki is equal to 0, and then we can solve the, this is your square term. So S I can write it will be minus R plus Kp plus minus, here I can say R plus Kp square minus 4AC. 4AC means 4, this is your A, this is your, let's suppose, B, this is your C. So we know this, if your AS square plus BS plus C is equal to 0, then we can see as we can write minus B plus minus B square minus 4 AC divided by 2A. So using this here, this is basically discriminant we called in the under root term. This is a root of a quadratic equation. So similarly, just I have written A is your, we can say this your Tp Kp R square into Ki divided by here 2 Tp into R. So this is, we are getting the roots of this. Now you can see this term is negative, this term is less than, because this is all positive here value, so this is again reduced. So even though if you are adding the positive term here, you will get the negative. So this shows that all the coefficients are positive. So this gives that all the roots will lie. So this shows that all roots here, two roots basically, they will lie in left hand plane of S plane. S plane we are talking. Now this discriminant here, that gives, it may be your positive, it may be a negative, it may be 0, means no value, all the values are here. Positive means here if this is more than this, it is positive, if this value is less than this, it will be negative, and if this both will be equal, then it will be 0. So the discriminant means that I can say here this value is the discriminant here under root term. If it is 0, means we can say if discriminant is positive. Positive when it will be, in that case it will be your R plus Kp square will be greater than your 4 Tp Kp R square into Ki. So this is a positive, and this will show that we are getting the non-oscillatory. This will give your non-oscillatory damped response. Another possibility that it is a negative. In that case, what we will get here, your R plus Kp, that is the square, is less than, here the value this 4 Tp Kp r square Ki, and now this will give your oscillatory. Why it is so? Oscillatory damped response. If this is less than this, you can see that we are getting the roots, imaginary roots. If this is less than this, means we are getting negative sign here, and the square root of negative is imaginary term. So what we are getting in this case, if it is a positive, we are getting all the, here this is your S plane. So in the first case, if it is positive, we are getting all this your roots on your this axis, that is a real axis. This is your imaginary axis, here it is your real axis. So all the roots are here, then it will give the non-oscillatory, means it will not oscillate, and it will give the damped, means damping will achieve. But here if it is a negative, means we are getting the roots here and here, and then it will be oscillatory. So we are having the imaginary terms, means we will have the oscillation frequency, and that frequency is decided by here how much negative we are having, and then our response will be the oscillatory. So this is called oscillatory damped response. Another possibility that it will be 0, and here it is called now non-oscillatory critically damped. What does it mean? It means if this is 0, means both roots, that is S1 and S2, they will be on the same point. Means here I can say that if I produce the dot point, so here both roots will be here lying at the same point. So it will be non-oscillatory, of course, because they are lying on the real axis, but it is called critically damped, and then we'll see here. For that condition, let us see for the critically damped. Here we are getting the value of Ki critical, and we are going to achieve, that is here R plus Kp square, that will be equal to your 4Tp Kp R square, and here it is your Ki, now this critical. Because others are fixed, only the Ki is set in such a fashion that we are getting this discriminant value is 0, and we are getting the critically damped non-oscillatory performance. So here we can say, if we divide here, we can again write this Ki critical will be equal to, I can say, R plus Kp divided by R, here it is a square, this value, and then we are getting 1 upon 4 Tp Kp here. So this is the critical gain when we are getting the oscillatory non-oscillatory critically damped. To see the performance, again I can see the subcritical values are required normally, and then it will be, if Ki is less than this K critical, what will happen? This is the critical when it is 0. If this value is less, what will happen? This will be positive, and this is a positive, then we will get the non-oscillatory damped response. So we will see here again what we are going to do, and if again this value is increasing, then it is going to be negative and negative. Once this is now negative, then we will get oscillatory. If this is a positive more than that, what will happen? If this Ki more, then this will be negative. If Ki is less, this is a positive. So we will see the performance here, what we are going to get here. Now you can see the performance, that is, I want to show this variation of this your change in frequency. This is your time, this is your change in frequency with respect to time. So what we are going to get here, we are going to get, let's suppose this here, if this value is somewhere, let's suppose critical, I can say, let's suppose this is your Ki is here is equal to your Ki critical value. Now if this Ki, as I said, the Ki is increasing, it shows that we are going to get the oscillatory response. So if this is the Ki critical, from that if you are still increasing, what will happen? You will get your oscillatory response, and finally here like this. So this is, you can say, change in Ki, just you are increasing. So this will give your the critical value where it is a critically damped, and others here is a critically overdamped, and we are keep on doing. Means here this value is Ki is less than Ki critical, and these values are Ki is greater than, for this here Ki is greater than Ki critical value. So this critical value is calculated, and based on that we set our controller so that we can get the proper response. So this is the dynamic performance, and you can see here we are just getting the 0 steady state error, but only just we have to see by setting the value of Ki, that is very very important, and that can be changed because it's a controller gain, we can change, and then you can say your performance time is also changing. Here this is the settling time is here, you can say the settling time here for this. So we want how much overshoot and how much quickly that it is settling this. So the Ki is very important parameter, and that is basically decided once we calculate the critical value, then whether we are going to increase or decrease, you can achieve the performance accordingly. In this whole process we have assumed several things, and now I can summarize this. What are the assumptions that we have made? First assumptions we have made that the hydraulic and the turbine dynamics, means your governor and your turbine dynamics, were neglected, but they can be included in the simulated of the graph. Means we can include them if you are going for the analyzing using the computer programs, you can include, and then you can see the performance. As I said, here what will happen, there the dynamics will be also included, and it will be some oscillatory nature, and finally it will be settled in the that time period. So first one is that we have included this your, you can say Tt, and we have neglected the Ts time constants. So these are the assumptions that we had made, and the assumptions are well valid because here the time constant of the Tt and the Ts is very less than the Tp, so we have ignored, and only the change here will be in the fraction of seconds. Second assumption that we made, that speed changer response was assumed instantaneous. Means it was thought that the speed changes, that is your governing system, it is instantaneously. Whenever it is required, suddenly it is given, but it is always it is not true. Also, third, we assume the all non-linearity in the equipment such as deadband. Normally, what is deadband? Means we have ignored, means non-linearity like deadband. You can see here we are having some deadband, and then your machine is so operating. So this is your deadband. So we have neglected all the deadbands, non-linearity in the equipment in this analysis. The fourth assumptions I made, that it has tactically assumed that the turbine can change its torque as fast as it is commanded, but it is not so. There is some ramp rate, means normally the megawatt per second. It is a technical characteristic of this machine that if you want to change 20 megawatt power, it will take several seconds. It is not instantaneously. So we have assumed that it will be when command is given, it will take care, but it is not so. So this is called the ramp rate effect, we ignored. Fifth assumption that we made, that is also very important, we have assumed that ACE is available as a continuous signal. This area control error, ACE, and this is ACE is nothing but your change in frequency. We have assumed that it is a continuous signal that we are getting, but it is not so because we are using some measurement circuits, and that measurement circuits basically depends upon the sample data acquisition. Means we are measuring at certain interval of time. So if your frequency here is for measuring this, means every point that we are measuring, and then we are calculating the frequency. So it was assumed that it is a continuous, but in reality the measurement of the frequency deviation, that is a change in delta f here, takes place discontinuity in the sample data fashion. If the sampling rate is relatively high compared with the fastest change in the response, then the above analysis, means this whole analysis, will give the good result. So we have to have the fast analysis. A very simple data should be very fast, means frequency should be very high, then we can say this analysis is valid. So far just we analyze this ALFC loop, again primary and secondary, that is the load frequency control loops for the single area system. But in the practice, it is not only a single one area system. We can have the different area system. They are connected with some tie lines. Then the performance of the system will be totally different. Then we have to analyze the other areas along with the primary area, and then we can see what will be the performance and what will be the advantage of having the tie line connection between the two different areas. So before that, let us consider this control area concept. Any power system can be divided into subsystems in which generators operate in coherent mode and geographically close to each other. I want to say that coherent means they are operating in the coherency, means whenever there is some disturbance, the oscillation of these generators are corresponding to same, because there will be deviation. Suppose there is certain change in the load, so the generators which are in the coherent mode, they will oscillate, and the relative oscillation between these generators will be 0. So that is called, it is a coherent mode, and also they must be geographically close to each other. For example, in a big power system, here this is a big power system, we have few generators, these are sites, and they are connected with some transmission lines here, the network, and there is some change here in the loading. What will happen? Their angular separation will change because they have to supply more demand. If here, and it is not a steady state change because they will be oscillating. To meet this, the angle delta will change, will settle, it will take some time. So the oscillations or rotation change or speed deviation is relative speed in among them is 0. Then we can say it is a coherent mode, and also they must be geographically close here. Then we can say this is one control area, we can have another control area, another control area here. So such coherent area is called control area where frequency is same, means here the frequency we are talking the same, similarly here the frequency is same, so we can have the different areas. The coherent mode, all generators operating in union. So in the multi-area system, the automatic generation control, normally we should divide the system into the different control areas. So the control area, the definition, just I am talking, the control area is a subgroup of power system consisting of coherent groups of generators bounded by geographical area. The boundary is nothing but a tie line points. Means here they are connected by some tie line, they are connected by some tie lines, and then we can say this is boundary. Control objective here are to maintain the frequency of this various system, to maintain net power interchange in the tie line to their scheduled value. So we have to just maintain the frequency of all the areas, and also to maintain the net interchange power between the two areas, interchange areas, through the tie lines to their scheduled value. How much interchange is permissible, that is a pre-specified. Now you can see this here we have shown this 4 area system, and all the areas are connected by the tie lines. For example, area 1 is connected with area 2 with this tie line, and the power which is flowing, this P12, that is going here. Similarly, this area 1 is connected with the area 3, and here power is again the tie line connection, and the power is flowing 1, 3. Here we are talking from 1 to 3, it is some value, it may be negative or positive. From the 3 to 4 we have another here, this tie line. From 2 to 3 we are having this. From 1 to 4 we are having this tie line, and 2 to 4 we are having this tie line. So all the areas are connected, and we know the parameters of each area is nothing but it's the combined inertia constant, that is H1, because there are the different machines, there may be 10, 20, 30 machines, so the combined inertia constant that we can calculate, let us, it is H1. The combined, the Tg1, that is a governing time constant, here the combined Tt1, that is the turbine time constant, here the Tp is the combined power system time constant of area 1, and Kp is, you can say, gain of that generator gain, that is Kpi of area 1. We also have some other parameters in this area 1, that is R, that is a regulation. We had the load, that is a frequency dependent loads, and related with the constant D1, and that is your bias factor B1, because they are related here, nothing but your, the B is nothing but your D plus 1 upon R. So they are changing, so this will be also changed. Now the net power interchange from the area 1, I can say it will be the summation of all the powers that they are going from this area. Again, this power is the, as I said, is algebraic sum, means here we can say this is your summation of the power from area 1 to the various area I, and here I is equal to 2 to various areas, that is your, let's suppose, n area. In this case 4 area. So I can say this, the net interchange will be nothing but your P12 plus P13 plus P14, because we are having 3 area. So the net that is going, it is the addition of all these powers. Some power may be coming, that's true. So here this, it is algebraic sum. So if it is value is coming, then it will be negative, and it is, so the algebraic sum at this boundary, and that is related here. Here we are not writing I is equal to 1 because the P11 has no meaning. So it is not a net power interchange, it is inside. So it is always here from 2 to n, means n is number of areas, and then we can write the net interchange of area 1, we can write here. Similarly, we can write the net area interchange of 2. It will be summation of P2 I. Here I is equal to 1 to n, but not 2. So what will be this value? We can write P21 plus P23 plus P24. So we can write the summation of the power here. Those are coming out, whether it is negative or positive, and then we can add together, and then we can get net area interchange. Now another, thus we have to, here for simplicity we can consider the 2 area system. Here the 2 area system has been considered, and then we have to model this tie line power flow, and this modeling will be included in your, that is a area load frequency control. So this tie line model we'll consider in the next lecture, that is lecture number 5. So now I can recap what we did here in the lecture number 4. We saw that the secondary, or you can say the secondary ALFC control loop were designed to remove the frequency error, and we saw the performance of this secondary ALFC loop, that in steady state we got the 0 frequency error, and that is required. We also saw the dynamic performance, that is dynamic step response, that we saw whenever there is a change in load, what will be the dynamics, and we derived that curve. And we found that the gain is very, very important. Here, as I said, this gain Ki is very, very critical, and that we calculated, and we saw this by setting this value gain we can get the different performances, means in terms of your settling time, difference between your overshoots, and this Ki that we calculated. But in all the cases we found that if we are using the integral controller, it is reset control, it is reducing our frequency error. At the same time, here we can see from this equation it is a stable control closed loop, and then we also verified here, you can see from this we say this is a stable, it is from this graph you can say it is stable, and we made the various assumptions, we justified that, that's how it is true. And now in the next lecture we will see if the 2 areas. So far just in this lecture up to the lecture 4 we discussed the single area. Now we are going to consider the multi area, and primarily I'll consider the 2 area, then we'll model the tie line models, and then we'll see how this blocks, now they are going to be added together, and what will be the advantage that we are going to have with the tie area control. Thank you.